Thank you very much.
So again, please tell me if I'm talking too quietly or if there is any problem. So today I decided to talk about mostly an example, which to do with reduction of this quasi-Hamiltonian, quasi-Poisson double. Just because and then I will also say something more general at the end and some other example. I must say in general I'm usually working mostly on examples. I like examples. And although this is not my latest work, but for myself it is seems to be interesting, and that's why I decided to talk about this. So I have more recently. So we already have seen these two kinds of so-called Ruijsenaar-Schneider or RS systems. And but here I mentioned two which we related to this talk. So there is the hyperbolic system. When there's two hyperbolic functions involved, dependence on momenta and dependence on coordinate. You know, if in special relativity the energy depends on rapidity in this way. So this is somehow the reason, one reason for experience of this kind of factor. And then we have seen when we have a trigonometric function. And we have also seen when here we have trigonometric and they're hyperbolic. And this hyperbolic version, as I mentioned, I don't know how to treat this one by Hamilton reduction method, although probably this is the most important one physically. And there is a so-called compact or compactified version in which dependence of the two sort of Darboux variables or coordinates and momenta, both of them are trigonometric. And so in some sense, the domain of the variables is compact because of the trigonometric function. But you see that it's kind of dangerous Hamiltonian here because of this minus sign under the square root. So what happens if somehow under square root you get something negative? And so this model needs some kind of completion of, so this is just a local description of the phase space, needs some kind of completion when the flows are complete. And such kind of completion was constructed by Simon Ruijsenaar in 95, assuming that this parameter x, which is just is in this range. And basically he said that let's suppose this one, and let's suppose that these differences of the particle positions are always bigger than x. They run from 0 to pi in my language. And then if this is so, then separately every square root, he wrote that separately everything is non-negative under the square root, and then he managed to to embed this local phase space into Cpn minus 1, and he managed to show that the model gives complete flows on the phase space Cpn minus 1. Okay, and then with my collaborator Szilárd Klimcsik, we found Hamilton reduction treatment of this model when this complete phase space automatically comes out. But also we just took this parameter x to be in the range which was considered by Ruijsenaar, just because we were interested in understanding his papers. Fantastic. Okay, but then later I realized that okay, from the Hamilton reduction point of view, there is no reason to restrict this parameter like that, and so we explored the case of the generic parameter with another colleague, who was a student at the time, and with another guy, and still this led to some interesting results, which are still should be further developed. Which actually this is a project which maybe I should work this summer. Read with somebody. Okay. So just kind of main slogan. Yes.
So if you say compactified, should I think of that as like Moser regularization of the Kepler, but now for that Hamiltonian, or is it like?
It is Ruijsenaar in such a way that there is this phase space, this local phase space, and he gives some kind of explicit embedding into Cpn minus 1, and then by the appropriate conjugation of flux matrix, he notices that the Hamiltonian everything automatically extends to full of 3 minus 1. It is that sort of thing. Really, it is similar. I like this kind of completion of little program, the completion of irregular system. The main slogan here, and this has to do actually with the lecture course on infinite dimensional symplectic geometry, that this whole thing has to do with moduli space of flat connections on the torus with one hole. What is a torus with one hole? For me, it's just we have identify the opposite paths, and there are some kind of A and B cycles here, and there is a whole. This part is removed, and then we have the relation AB, A minus 1, B minus 1 is equal to gamma in the fundamental group. I mean, we can this curve is the same as the curve around the hole, and consider flat connections with this principal connections with the E to P, and then this gives a finite dimensional phase space, and one can fix the conjugacy class of the holonomial of the connection along that I mean the boundary of the hole, and this is supposed to give some sort of Poisson manifold, or basically symplectic manifold, and so this phase space, or the arguments that in an invertible phase space will be group manifold times itself, elements 0 to A, B, and this kind of constraint will be this is a moment map constraint. I put moment map, not momentum map. Also something which corresponds to fixing the holonomial along that boundary of the okay, and then take quotient by the isotropic group of this moment that mu 0 is a moment value, and then we obtain this moduli of flat connections, and then the invariant functions of the two matrices A and D, which are the holonomials on the two cycles on the torus. They give two abelian Poisson algebras. Yes?
Is there a big difference if I only take semisimple? I mean, is the center here maybe how big it is? Or is it...
You mean semisimple? This can be semisimple, yes.
Yeah, but is it a big difference? Or?
No. But I am just... okay.
Okay, fine. So what is this talk? So first I recall this quasi-Hamiltonian, quasi-Poisson geometry, which is I mean, there are not only there is moduli space of flat connections on some surface, and there are some finite this is some fine result of some finite dimensional Poisson manifolds at the both construction, but there are some finite dimensional null spaces in between the infinite dimensional one and the final Poisson manifold. And there are various such finite dimensional models. There is some kind of Fock-Rossley type model. And there is the quasi-Hamiltonian approach of Alexei Martin and Meinregen to this modular space of flat connections. We led to, or which is the main motivation for this Alexei Martin Meinregen. I don't know whether this was mentioned in previous lectures. Maybe it was by Alexei, I don't know. So I will recall this theory, and then I will apply it to some specific reduction, which will be the group will be SUN, and I will choose specific moment value parameterized by that number X. And then I will sketch the result, derivation, etc. Maybe I will say something about how you directly embed these things into CPN, but that's kind of involved, and at that level I have also elliptic generalization of these trigonometric models, but not at the reduction level, just direct construction. Then maybe I plan to talk about this appendix, but we will see whether I have time. Okay. So now everything which I say, a couple of transferences or slices due to Alexander Martin and Meinrecken. So it's just a recall of definitions. So it's not important that G is a compact group in the general theory. It can be anything in which the Lie algebra has an invariant bilinear form, invariant non-linear bilinear form. But I take it to be, just for my purpose, this will be. Okay, so let's suppose that we have a G manifold M, and there is an invariant 2 form. This is called the quasi-Hamiltonian 2 form if there are some further data. And namely, there is a moment, there's so-called group-valued moment map, which is supposed to be an equivariant. First of all, it is an equivariant map. So it satisfies this condition for the group action on the target and the source. Then the exterior derivative of this 2 form is not 0, but it is obtained by pulling back this famous 3 form from the group manifold. Of course, this is kind of matrix notation, so you have there the Maurer-Cartan, the left invariant Maurer-Cartan 1 form on the group manifold, and so on. And then this is the zeta. Zeta is an element of the Lie algebra, and the zeta m is the vector field on the manifold which generates the action. So it is supposed to be related to this 2 form and the moment map by this equation. If you know the Poisson theory, then there would be only one of these left and right invariant ones there. So it's related to Hamilton. It's somehow analog of that this would be Hamilton ordinary to the Hamiltonian vector field, and you would have the exterior derivative of the corresponding moment map component. And then there is a condition on this 2 form is not, in general, it's not non-degenerate, but it's almost its degeneracy is very much controlled, Namely, let's suppose that little m is a point of this manifold, and the kernel of this 2 form is given by, at the point little m, it is given by these, the vector field, the values of the vector field corresponding to Lie algebra, and those Lie algebra elements which belongs to this kernel, that is the eigenvalue of this moment map value with respect to the adjoint action on the Lie algebra with the eigenvalue -1. Okay, so the kernel is precisely given by these vectors.
Yes. Conjugation.
On the Lie algebra or the adjoint action. Okay, so here this is the inner product. It's not important, but in the original paper they take it positive definite, and in my application it's not important, but I will take it positive definite later. Okay, and yes, this phi is, as I will mention, this I denote by phi the action here. This is vector field, and this is how it is defined. In their paper, they put a minus, or in various papers, there are various conventions for these vector fields, plus or minus, but this is how I use it. So now, if we have such a quasi-Hamiltonian manifold, the main point is that if you have a G-invariant function, real function, smooth function, then this defines a kind of dynamics in the same, basically the same way as any function on a symplectic manifold. Namely, I prefer to put this into the second argument. This is supposed to age this function, G invariant real function, and this is kind of analog of Hamiltonian vector field, this VH. So it satisfies this usual condition. In addition, it satisfies that this means that if you take the integral curve of this vector field, then the moment map is constant along the integral curve. And then this uniquely, they prove, the Alexei Mark-American, they prove that this uniquely determine this vector field. And then you can define this kind of quasi-Poisson bracket for two invariant functions. Of course, you can also define it if one of the functions is invariant, then then you take the derivative of the one function with respect to vector field. But the point is that this is an honest Poisson bracket on the space of invariant functions. This is the point. And so this quotient space, if this is an honest manifold, then this is a Poisson manifold in this manner. And this is nothing but this moduli space of flat. In applications, it can be applied to describe the moduli space of flat connections or Riemann surfaces with various holes and so on. So I think this is a really beautiful formalism. Okay, so well, it's okay. So basically, one can work with invariant functions in the same way as with any arbitrary functions of symplectic manifold. And there's also analog of Marsden-Weinstein point reduction or other reduction procedures has analog in this context. So quasi-Hamiltonian reduction. Suppose we take an invariant function and then we pick a moment map value, and its isotropic subgroup is G mu 0. And this is the inverse image of the moment map, which I call constraint surface. And let's suppose that this constraint surface is an embedded submanifold. And let's suppose that the quotient space of the constraint surface by the isotropic group is a smooth manifold, usual way. And because there are usual sufficient conditions to guarantee this. And in that case, in the quotient space of the constraint surface by the isotropic group, this is this projection, smooth submersion, there is a reduced symplectic form which is reduced Hamiltonian, which satisfies usual relations of symplectic reduction. And and then the same algorithm, how you obtain the flows of the reduced Hamiltonian, same algorithm. You take the original flows, original integral curves, they restrict to this constraint surface, and we project them to the reduced space. And And the nice thing is that this actually leads to some interesting examples. There's also some slogan. They say that Alexeyev, I was from Alexeyev or some people, that every interesting Poisson manifold is coming from modular space of flat connections. New slogan, relatively new. The important example for which I will be dealing this, which has this kind of strange name, internally fused double of the group G, but this is just this Cartesian product as a manifold. And the action is just by this diagonal conjugation. This is the group action. And this is the two form. So it manufactures out of pullbacks of Maurer-Cartan forms on the first and second copy. There's also this product. So complicated. The moment map is just this group commutator which corresponds to this situation on the torus with the hole. Okay. So this is the internal fused double. Now actually, there's also another development which I want to mention, which is due to Alexeyev, Kosman, Schwarzbach, and Meinreken a little bit later, the quasi-Poisson setting. So it turns out that on every quasi-Hamiltonian manifold, there is also a G invariant bivector P which satisfies certain conditions. And the condition, this is the Schouten, how you pronounce it, I don't know, Schouten bracket of the bivector with itself. And phi. Now, if you use I use a pair of dual bases of the Lie algebra, and this is actually valid for any invariant bilinear form. Doesn't have to be positive. So So this EA is the basis of the Lie algebra. And that is this sort of object. Okay? And the phi m means that for every Lie algebra element, you replace by the corresponding vector field on the manifold. So this is then a vector, or how you call it, on the manifold M. And the Scout M bracket is satisfied non-zero, but it is this. It is related to the group action in this way. And then you can define quasi. If you have this condition, then of course out of the bivector you can define some bracket of functions. And this bracket again satisfies the Jacobi identity for invariant functions, because for invariant functions this vanishes. And there is also a moment map condition can be reformulated in this manner that this mu is the moment map, f is arbitrary function on our manifold, little f is an arbitrary function on our manifold, and capital F is a function which depends, which function group manifold. So it gives a function. I mean, we can consider functions of the moment map. So this means that this is the function of the moment map, and this quasi-Poisson bracket is given in this way when it is expressed in terms of the left and right invariant vector fields on the group manifold. So the moment map somehow governs the Poisson bracket with the quasi-Poisson with any function with the moment map is given by this kind of formula. Okay. And then there is also a compatibility condition with this lowering of the index and raising of the index, which is this flat and sharp symbols, which is very easy to remember for physicists who are used to these indexes. Obviously, this is the origin of this terminology. So it is. So they are not inverse of each other, but the correction is totally controlled by the moment map and the action. And actually, it is also true that the image of the, I mean, out of the quasi this bivector, you get almost the tangent space of the manifold, but the tangent space of the manifold at any point is spanned by these vectors and the vector fields elements, the elements of the vector fields which generate the action. Okay, so one can also talk about quasi-Poisson manifold, just abstractly saying that there is a group action and this kind of. So I mean, not every such quasi-Poisson structure comes from a quasi-Hamiltonian one. But for every quasi-Hamiltonian one, there is such a structure. Okay, and now on this double, actually there are two interesting. Maybe there are more, but for me there are two interesting bivectors. This one. So this refers to just for simplicity, this refers to an orthonormal basis of the Lie algebra. So I'm using positive definite invariant form. This means that the right invariant vector field on the first copy, and second copy. There is this formula, and this is the one, this PD, which corresponds to the 2 form in the way I described in the previous slide. Okay, and there's another one, which is. Which also satisfies that the Scout M bracket of this with itself is the same as with the previous one. So it defines some quasi-Poisson bracket, which is Poisson bracket for the invariant functions. And actually, these two, if you view them carefully, you will see the only difference is that here you have here plus sign and you have here a minus sign. But nevertheless, they are very different. The second one. Is not non-degenerate and does not come from a 2 form. This is actually, I reveal it, although I will not talk too much about it, but actually this is, I have this kind of in previous talks, I was always talking about some map psi, my manifold to another manifold. This was the map of constants of motion. And in this case, this map is from G, there is this kind of map also in this case, although I will not be talking much about this. And in this case, here we have PD, and here we have PDC. So this is the space of constants of motion. There is this bivector. And this is the quasi-Poisson mapping in this case. But I will not be talking much about this. Okay, so for the second one, there is this is the moment map. It's a different moment map. Okay, so I will be mostly dealing with this quasi-Hamiltonian double, so the non-degenerate one. And I'm a little bit behind time, but so I want to mention the mapping class group action on this double. So this mapping class group. So the component of the identity of orientation preserving diffeomorphism of this torus with one hole. This is known to be isomorphic to SL2Z. Dane twist and diffeomorphism, which exchanges the two cycles of the torus. And the point is that this group, so you can view as these are generating elements of SL2Z as matrix group. These are the defining relations, SL2Z. And this group actually acts on this double by this kind of map. So the point here, maybe this is not very important, or it's important, but we don't need it so much. So that basically you see that it exchanges the A and B cycles there. And this goes down to the quotient space, and this really gives an action of SL2Z on the quotient space. So it preserves the two form, it's equivariant or invariant with respect to the action, and preserves the moment map, so on. And the relations are not satisfied on the double, but they are satisfied up to gauge transformations, and they descend to the reduced space. And this is just some kind of description of action of mapping class group on this representation variety, which really comes by acting by the diffeomorphism on the flat connection form at the Abbott language. Okay, so I will be dealing with now what kind of so I'm interested in finite dimensional integrable systems. So what is the unreduced system? So as I already mentioned, that I have two Abelian Poisson algebras on this finite dimensional phase space. Namely, let's take the invariant functions on the group manifold, real invariant functions, and well, they give rise to two functions on the double, either the pull back from either the first vector or the second vector. Okay, and I already mentioned that these are two Abelian Poisson algebras. And what are the flows? The flows are very simple. For such a function on the group manifold, you have the Lie algebra value derivative. Since the invariant function doesn't matter whether the left or right derivative is the same. Left and right derivative is the same. And the corresponding integral curves to an initial value, well, it is the usual thing. That it is just orbit of one parameter group like that. So the point is when the Hamiltonian is depend on A, then A will not change along the flow, but the other guy will change like that. And if it depends on the second component on B, then B will not change, but A will change like that. Okay, and so we obtain on this Poisson space, we obtain two, but this is not a smooth manifold. We obtain this Abelian Poisson algebra, also with a fixed moment value, we obtain such thing on the reduced phase space. And they are interchanged by the action of this generator of the mapping class group. A and B are interchanged. Now, so this was a general review, which I did it slowly, but it's okay. So now I come to the thing which I'm interested. So let's take SUN, and I don't like this 1/2 there in the, but for some reason maybe my collaborator is responsible for this. Now I keep it because I'm using my paper for the conventions. Now I would not put 1/2 for sure, but okay, in the positive definite inner product. And this is the moment map value. So you can recognize this is analog of what we had in the previous lecture. It was a diagonal matrix, but with real positive entries. Now just two different eigenvalues. And I assume that some eigenvalues are excluded because it turns out that the action of the little group, the isotropic group of this moment map value, is free on the constraint surface if this condition holds. So apart from some finite number of values of x, the action on the it's not the action of by the center, of course, x obvious trivially, but apart from that, the action of the isotropic group is free on the constraint surface. And then it is known that if this group is, because of the group is connected, simply connected, the inverse division moment is always connected. This is known in general. And because everything is compact here, so if the action is free, so we know that we obtain compact, connected, smooth reduced phase space. And by counting the dimension will be 2 times n minus 1. So we have, on the group, we have the invariant function, the functional dimension is n minus 1 for on SUN, the rank of the group. So we expect that basically we know already at this stage, if we know that this action is free, that we are going to get a Liouville integrable, or two Liouville integrable system from the two possible Abelian Poisson algebras. If they remain independent on the reduced phase space, but they do. And it turns out that in terms of the suitable coordinates on the dense open submanifold of this reduced phase space, is the simplest invariant function, real part of the trace of A, is this kind of Guizner-Schneider form. Then the other variable, the Q, they arise from the eigenvalues of the other matrix B. One matrix gives the interesting Hamiltonian, the other matrix gives the sort of particle coordinates, which are also supposed to be an Abelian Poisson algebra. And now I'm going to describe what kind of results we have, and then I a little bit talk about sketch how we obtain these results. And so in order to somehow characterize the reduced system, we need to reveal what is the content of this constraint. What does this imply about the matrices A and B? So we need to determine basically the spectra of these matrices, the invariant functions, the spectra of these matrices. And there are two qualitatively different cases. Either this moment map constraint forces us to be in the regular part of the group, which means that distinct eigenvalues for SUN. And it's because of this mapping class group action, if one of the matrices is constrained to be in the regular pattern, also the other one is constrained. So there are in principle these kind of cases, or I call type 1 cases when this happens, and type 2 cases when this does not happen. So when the eigenvalues, when the conjugacy class of the matrix can reach the boundary of the Euler curve. Okay, so in the first type of cases, we obtain that our reduced phase space is a Hamiltonian toric manifold. So it means that we already know that it's connected, compact, the dimension is 2 times n minus 1, and simply we obtain an action of effective action of an n-1 dimensional torus. And we know that such a manifold is characterized by the image of the torus moment map, the moment polytope. And actually, the way we analyze is that we try to find this polytope. And so this is one case, and the other case is different because we cannot because these torus moment map comes from the eigenvalues of one of the matrices, and if it reaches the bound, if it loses its regularity, then this is no longer differentiable. So we don't have such a torus actually in the full phase space in the type 2 cases. Indeed, so in the type 1 cases, these we call them spectral functions at the time when we wrote our paper. They are smooth functions. There are some spectral functions which are basically eigenvalues, or representatives in the Weyl curve, really. Then they are smooth on the regular part, but only continuous at the singular part, when the eigenvalues can coincide. And the eigenvalues A and B, they give this kind of functions, and this means that when we are not contained inside the regular part, then it means that either from one point of view the action variables are not defined globally, they are subfigurated. From other point of view, the particles can collide, because the eigenvalues of one matrix are the action variables, the eigenvalues of other matrix are the particle positions, and the so-called Ruizen duality is that these two can be exchanged. Okay. So this still, okay. And what are the spectral functions which I was talking about? So let's define this matrix. You can recognize this as a fundamental matrix representing fundamental weight for the SUN. So this E are elementary, n by n elementary matrix with only one single entry, which is non-zero at the one JJ position. And okay, and every element of SUN is conjugate to a unique matrix of this form. And when these psi's are from R at n-1, satisfying these conditions, that they are positive and this one is smaller than pi. So this is, you can recognize it in Lie theory, this is this Weyl description. And there is this two here just because this has to do with 1/2 in the invariant scalar product. Okay, so every group element is conjugate to unit matrix of this form, so we can define an invariant function on SUN in such a way that they say this capital psi K in this diagonal matrix is just a little psi, and it is supposed to be invariant, and then its unity defines it. And this is actually an analytic function on the regular part of the group. Okay. And okay, and then we have two kinds of functions. It's alpha K, I mean, it depends on A and B, that we take the spectral function of the matrix A, or we take the spectral function of the matrix B. And the main thing is that when we are on the regular part of the double, the two matrices are regular, then these functions define 2 pi periodic flows. I can just compute their I just need to compute their derivatives, and the derivative will have to do with standard SL2 generator corresponding to simple roots and easy to calculate it. So it means that when everything is regular, then we actually obtain 2 toric moment map on the reduced phase space. And our main result is that we can see for what values of the moment map value had a parameter in it. Varies between 0 and pi with some values excluded. And we can see we were able to show for what values of x is it true that the constant surface is contained inside the regular part, in which you are bound to have toric manifold. And maybe for some values it is not so. the result was very surprising and very strange, very strange. And but this is the result of a proof, a long proof. This is the kind of main result. So let's suppose that so the type 1 case is when we have, I mean, everything is regular. Type 1 values of the parameter x. Let's suppose, so what are those values? Let's suppose that we take two integers between 1 and n minus 1, such a way that they are relative prime to n, so that the greatest common divisor is 1, and the product is c times d is 1 modulo n. So if c is such that the d exists uniquely. Let's suppose that we take this such a c from 1 to n minus 1, which is relative prime to n. And this is supposed to describe this is some kind of open interval, which is c over, pi is here, c over n, from c over n to this other value, the right hand part of the interval. This is the left hand part of the interval is smaller than c over n. And okay, there's some finite number of x. So c over n is, for example, is an excluded value, because there's a finite number of excluded values. So the claim is that if the x, the parameter of the moment map value, is in this interval around pi times c over n, then it is a type 1 case. Everything is regular. And if it is not so, then this is not true. And this was very unexpected because, well, I mean, we already knew the case when this x is between 0 and pi over n. This was always an original case. Everything is regular. So this is an illustration of the result for various values of n. The n equal 2 case is not written there because it is kind of too easy. So here the red, so this is pi, the range of x over pi. So x varies from 0 to pi. So what is the black points are excluded values. And here you have some red intervals. For instance, n equal the c is 1, then there is this 1 over 5, and there is this red interval below and after. This is type 1. The red is always type 1. And the blue is type 2. So the type 2 cases start to appear where n is at least 4. N is 4. But it's so it is very intriguing, let me put it this way. And so this is the classification result. And then it turns out that if when we are in the type 1 case, then the moment polytope is some standard simplex, and this compact reduced phase is just Cpn minus 1 with a certain multiple of the standard Kubin's 2D. I don't know how to pronounce their name. I mean the standard 2 form. And so how we found this kind of classifications? Let me try to sketch this. Only sketch. So let's look at this hyperplane. There are also only n minus 1 psi values, but I can make n of them. Everything is positive. Sum is equal to pi. And there is okay. So this is this corresponds to this is actually the simplex which is Weiler curve correspond to exponentiation after the Weiler curve. So okay, I just repeat that every SUN element is conjugate uniquely to an element of this form. Now, just now, for the moment, out of the blue, let me define X is parameter, let's define this ZL as a function of psi, given by some X-based formula. Lot of sinus functions. And there are, and L varies from 1 to n. And this L counts modulo n, so I can define it for any integer, but from 1 to n is interesting. And then our basic lemma is that, let's suppose that the psi is in the interior of this simplex, interior of the Weil alcove. Then there exists solution of the moment map constraint. This is the moment map constraint, just B is written on the right hand side. There exists a solution of the moment map constraint if and only if all these functions are non-negative. And this was obtained in the following. And then one gets to analyze and what points are these functions non-negative, and this gives this moment polytope. So basically, the basic thing of the proof is just this, that we have this equation, this is the moment map constraint. Let's conjugate, we can conjugate this equation by some group element G. Everything conjugate A and B. Then A goes to AG, the B goes to this diagonal matrix delta psi. And now the point is that this mu, because this special matrix is mu 0, it has only two distinct eigenvalues, 1 multiplied by 1. So this matrix G mu 0, G minus 1 is a matrix of this form. When this is unit matrix, so this is unit matrix plus rank 1. When this V is the last column of this matrix, so it is a vector. And so this V is a vector. And now if you put in here this matrix, then you can calculate the characteristic polynomial of the left hand side and the right hand side. They must be equal because there is equality. So on the left hand side for the characteristic polynomial you obtain this, because this is diagonal matrix, and this delta J is just the diagonal matrix elements, delta 1, delta 2, delta n. And on the right hand side, because this matrix is very special, you can also calculate the characteristic polynomial, and it is this. And then if this delta is a regular matrix, if all the eigenvalues are different, then you can evaluate this at n distinct points of the lambda, the variable in the characteristic polynomial. In evaluating it at specific distinct values, you will see that from this sum only one terms. This is you don't see it immediately, but this very much simplifies, and simply you can see that the square of the modulus of this component of this vector is this function. And this function, of course, this is because this is the square of the modulus of something, this must be non-negative. And then, so this is how you find that this is a necessary condition for the existence of solution of the moment map value with the eigenvalues of the matrix B matrix being conjugate to this one. This is a necessary condition, but then it turns out that you can turn this machinery backwards, and then it's also sufficient. And so what we say that okay, so we call configuration space. It's just a name because we are thinking about particle positions. The configuration space is just those psi values in the interior of the Weil alcove when these functions are non-negative. And actually this is also the sort of the range of the would-be action variables for the eigenvalues of the other matrix. And then you simply we have to look at sorry, I want to go back one. So we have to look at this function and how this function can be positive. And obviously it can have some zero because of this sinus here. So it will vanish in some hyperplane. And the hyperplane will change sign. And depending on whether this prefix is positive or negative, there could be one or two sign changes of this function. So it is, but basically, this is the whole idea that we have to look at the signs of those functions, and which changes sign in some planes, which will be the bounding hyperplanes of this polytope which we are after. And we find that if, let's suppose that C is just any from any integer from this range, if this x is x, the parameter is from this range, then this so-called configuration space is the intersection of two polyhedra. And the intersection. And both polyhedra, these are n minus dimensional affine space. N minus one dimensional Euclidean space. So there are defined by there are n hyperplanes in this n minus one dimensional space which define this polyhedron. Like in a plane, you have a triangle, then it is defined by three sort of lines. Or if you have a tetrahedron in three-dimensional space, it has four things, and so you have four planes. So, but here you have two such polyhedra, and intersections two polyhedra, and it turns out that when the parameter x is in this range of type which you call type 1, then one of the polyhedra is a standard simplex which is contained inside the wide chamber and inside the other polyhedron. So, so in those cases, we just can calculate totally explicitly what is this configuration space, and it turns out to be the standard simplex. And because of the Delson theorem, or then we know that it is Cpn minus 1. We can also explicitly map this into Cpn minus 1. Okay, and in the other cases, okay, so but let me talk about the other cases a little bit later. So just very quickly, so because I'm talking about Ruiz-Anal systems, so what about interpretation? So this plus part of the configuration, all these functions are actually positive, not non-negative but positive. So in that part, actually we can write some explicit matrix here depending on the psi and theta angle variables, n-1 angles, totally explicit matrix depending on what we want, and then this G matrix which I defined here, just a matrix for which just a special unitary matrix for the last column of this vector which we were talking about, and then this is I mean, this is an element of the moment map constraint. This is an element of the moment map constraint surface. Or moreover, I mean, if the parameters are here, then this is a global cross section of the isotropic group actions in the moment map constraint surface. On the dense open part, and those functions are positive. So it's not really local; it's kind of semi-global, or the dense open part. And then these are Darboux coordinates, and actually the psi is actually action variable. Sorry, it's from my point of view, it is a position variable of the Ruiz-Schneider model, but it also defines a torus action. And so we have this thing, and then we write. I mean, then we write this psi is contained in the matrix B, and now let's compute the real part of the trace of the first metric A. Then this is this Hamiltonian, which is a Ruiz-Schneider type Hamiltonian. if we introduce new variables for interpretation, I'm almost finished, and there will be no appendix. I'm sorry, I thought that if time permits. So if we write this delta k as directly like that, then everything if we conjugate, then this Hamiltonian really takes the form which I promised, this Ruijsenaar-Schneider type. And indeed, this is also some kind of interpretation when, for the type 1 cases, when the parameter like that, then this means that the particle positions are somehow, because the psi j is the difference, the angular difference between particle j and j plus 1 on the circle. So there are some kind of sort of picturesque interpretation of these conditions which define these hyperpairs. Okay, and I don't talk about this, but we also can explicitly embed this into Cpn-1, and actually these psi's become the usual moment map as you sort of these are the embedded into C, then the image will be this sphere and then we can explicitly extend our Lux matrix to Cpn-1 very shortly, and then we can sort of explicit embedding into Cpn-1, and then since in the explicit embedding everywhere these functions appear, these trigonometric functions. So then we notice that, okay, so if we replace the trigonometric functions by some elliptic functions in this explicit embedding, so I'm not showing the detail, although we are not supposed to understand this. But we replace every sinus function by something to do with Weierstrass zeta function, this S function, which is not Weierstrass zeta, but is similar to that function. It is, or sigma, sorry, the sigma function. It is differs from sigma function by some exponential. And anyway, we can define for every, when the parameter x in the type 1 range, then we can also define an elliptic version of this model. And for the type 2 cases, we really don't know. We only calculated the smallest n for which type 2 case appears is SL4. So this polytope in the standard case is a tetrahedron. Tetrahedron has four vertices, and every vertex has 3 edges. Now we found that in this example, this polyhedron has actually, instead of 4, 8 vertices. And 4 vertices are contained inside the Weyl-Jacob and 4 at the boundary. And at the boundary, at every vertex, there are 4 edges coming from the vertex. And so it's not, of course, it cannot be a Delson polytope. It's some kind of different polytope. And so this is one of the projects which I mean, if I have enough energy, it would be interesting to explore these type 2 cases. These are the references. And actually, I already mentioned at the beginning that actually I have the same kind of, I can have the degenerate integrable system. This is the principal orbit type for the action on this internal flux double. And I have the same story as for the cotangent bundle and the Heisenberg double, just I decided not to present this because this would be already too boring. So the type 2 systems should be understood. What kind of singularities? If conjecture, probably elliptic singularities, but we don't really know. And also the quantization of the type 1 system has been worked out both in the elliptic and trigonometric case, but for the type 2, basically nothing is known.